today we are very happy to have Professor Paola Caselli to ASIAA. Paola is the director of Max Planck Institute of Extraterrestrial Physics. She got her PhD in 1994, studying molecular spectroscopy in the University of Lima. And then she continues. She's expert in some emitter wave observations, including single dish and also interferometries. And she's also an expert in laboratory astrochemistry, setting up a lot of fancy experiments in Max Planck Institute. And she's also our faculty panel member. We're very happy to have her here, and also she will give another talk in the S1 meeting this weekend. So let's welcome Paola.
Thank you very much. I'm very happy to be here, and thank you for the invitation. So today I will give you a talk a little bit more specific about fractionation. And for those of you who will be at Kaohsiung, starting from tomorrow, you will see also some other things we are doing at MPE, but today I will focus on this fractionation, and I just wanted to motivate a little bit the work. So why we are working on this deuterium and 15N fractionation? Well, these are markers in a sense of the history of say star forming region, protoplanetary disk, and ultimately planets like our Earth. As we will see, also our oceans are deuterated, so the D over H is higher than the cosmic D over H, so we want to understand why, and it seems that the reason comes from the history of, say, this chemistry that went through whole way back when our solar system was a cloud. And these are the starless cores and the prestellar cores. So here is just a little cartoon showing this is supposed to be a very big, say, core, dense core, fraction of a parsec, and then you see you have the formation of the protoplanetary disk and the young stars, and then this protoplanetary disk will then evolve in forming stars. The connection to the solar system is due to the fact that, again, this is another artistic view of what some people, in particular, this is kind of from NASA Goddard, people at NASA Goddard imagine our Earth at the very beginning. So after the moon formation event that happened a long time ago, about say 4.2 billion years ago, you had a very hot surface magma ocean, and then it started to cool down, and you have at that time also a lot of incoming bodies that bring in probably not just the water, but also complex organics that maybe have been very important for the formation of life. And this is one thing that we are interested on the, say, formation and evolution of these organics. These objects that actually we are witnessing nowadays, when we look at primitive material, we see that they contain also fractionated region where we have enhanced deuterium and enhanced 15N locally. So this is the whole, say, motivation and connection. So what I will then discuss today, I will show you how this deuterium fractionation happens, what is the starting point, our understanding of the 15N fractionation. This is still a little bit work in progress. It's not so super clear. The defractionation is better understood, I would say. Then I will show you some link to the solar system, and then the remaining puzzle. Now I put here this beautiful view of the ocean, not because, well, I love ocean, and I love, yes, sky. I love everything that is on our Earth. Oops, this is not a good idea. The reason is that the ocean, as I said, is indeed shows fractionation like here. So the ocean, we have water and heavy water, HDO and H2O. So when you take the ratio, the equivalent to D over H is actually 1.5 times 10 to the minus 4, and this is 10 times larger than the D/H cosmic. The air, where we have 78% of our Earth air in 4/2, and you look at the fractionation, well, yes, it is also that. It's fractionated. We have 14N over 15N. It's about 272, and this is, say, 3 times, say, 3/5 times, so of the 14N over 15N protosolar. So this is where we start with. So you see here I have cosmic because deuterium and hydrogen have been formed during the Big Bang. Here I have protosolar because for the nitrogen you need stars, so stellar evolution in the galaxy. So 4.5 billion years ago, when our solar system was formed, this is the ratio that, so you expected something like 400, 300 and something in the 15N. So let me start with the deuterium fractionation, and feel free to stop me if I say something that is not clear. I'm still slightly jet lagged, so I apologize if I say something that is not totally correct. I'll try my best to focus. So D/H ratio, so I already mentioned to you, but now I put here more objects in this slide. This is a slide coming from Hartog et al. 2011. And in fact, Hartog is, in this paper, you find the measurement of the D/H ratio in water in a comet that was observed with Herschel, and they found that this value is exactly the same as the one on the Earth ocean, so which was very exciting because now here, just look at let me explain first. So this is the protosolar value. So the value, or we say ISM, interstellar medium, the value that we believe we started with when the Earth, our solar system was formed. Here are our giant planets, Jupiter, Saturn, Uranus, and Neptune. So you see that already Uranus and Neptune have a little bit increased in deuterium. But then when we get to Earth, so we have to go above 10 times, about 10 times the protosolar value. And you see that there are 2 dots here that are spot on the same value. One is the one comet, which was this Hartley 2, and the others are the so-called CI carbonaceous meteorites. So these are the primitive material I was telling you before that contains water, deuterated water at this level, but also volatiles, organics, and lots of prebiotic molecules, which is, I will not talk about it today. This is one of the moons of Saturn, and here we have all the comets where the measurements have been taken, and you see that the majority of the comets, including 67P, this is the comet that was say visited by Rosetta, so these are very precise measurements. That's why you don't see even the error bars here. These are higher than Earth, D/H, and this is a little bit so. In the community, there has been some debate about what brought the water to Earth. Was it the carbonaceous chondrites? Yes, because it's very similar. Or the comets, well, it is a bit too high. But you know, our Earth has evolved since then, so I don't think that the mixture of these, besides we have a comet that has exactly the same value, it will actually be so wrong. So we will probably have this heavy bombardment that bring this water and deuterated material on Earth. And of course, then the question is, where does deuteration come from? One thing that was done in 2014, and this is a paper by Ilse Cliff, Ted Bergin, and collaborator, they actually studied theoretically, starting from a protoplanetary disk, and they asked the question, can we reach values of deuteration in the water similar to the one that we have on Earth, starting from scratch, starting from, say, this protoplanetary disk, and let it run the chemistry? So the answer was no, and the reason was that you actually need to bring in the ice and the gas that is produced earlier than the disk. So this is now the cloud within which the disk and the star has formed. So the conclusion, one of the conclusions of this nice paper here was that indeed the pre-stellar core chemistry is important. So we need to go back one step to actually understand this deuteration Of course, if all this is true, it means that some of this material that is made in the cloud just before the star is formed is preserved partially to the point of, say, planet formation, our planet. So now we go into a prestellar core. So zooming in, this is a map that was taken in the continuum, 500 micrometer with Herschel, showing a molecular cloud in Taurus. We are actually at this extreme end of Taurus. And here there is a peak, and this peak is due to a, say, agglomeration of material. So we have here a dense core, and that is why it is so bright. And if we zoom in here, now we have something that is 15,000 AU, 20,000 AU in scale, and this is our, say, prestellar core. What do I mean by prestellar core? Prestellar core is actually a subset of the more general term of starless core. So you know that in our galaxy there are molecular clouds. Within them there are fragments of molecular clouds that are dense cores. Those that are not associated with stars are called starless cores. And then there is a specific subset of them that we call it prestellar core that are particularly centrally concentrated. These are regions that are really close to form a star. That's why we are calling it prestellar. And we are so sure about that because they are contracting. So unless there is a big shock waves that destroy them, but there is nothing big nearby, they are going to form one or probably two stars. So we don't know yet, and probably some protoplanetary disk and then planet. Okay. So the difference is that the prestellar core are denser than starless cores. So the central density is about 10 to the 6 on average per cubic centimeter. So these are talking about H2 molecules per cubic centimeter. And in the central region, this is what I call the deuteration zone. I will explain to you why this is the case. So this region here where molecules, as we will see, will turn into ice because they just go meet with dust grains, freeze, and stay there. And this is the region that actually produces all this deuteration. And then, of course, there is the dark cloud zone that connects to the cloud that is traced by other molecules. Now, what we know about the prestellar core is that they are very cold. This is work that was done in 2007 by a student at that time when I was in Astrochemical in Italy. And what we did, so Antonio Crapsi, he actually did observations with the VLA, and using ammonia 1,1 and 2,2, and with the interferometer, we were able actually to go through the center of the core. This is the distance, so this is the impact parameter, distance from dust peak in arcseconds, so it's not really the radius. So, but these are observations, of course, but you can see that unlike the single dish here gives you a temperature in the center of 8 Kelvin because it is, of course, weighted by the warmer material that is around the central region. But with the VLA, we could actually go to the center and arrive at, say, in the central region where the temperature is actually 6 Kelvin, which agrees very well with models of radiative transfer of spherical clouds with the density gradient and illuminated only externally by the interstellar radiation field. So here we have 6 Kelvin, densities, as I told you, 10 to the 6 per cubic centimeter or more. And then what happened in this case? Well, you have a lot of freeze out. Molecule really freeze out. We did this in a long time ago with the CO, but also recently with other molecules, finding that more than 99% of species heavier than helium are actually frozen in the central 2000 astronomical units of this region. So you have a zone where you are actually going to form your future pseudodisk and disk, where everything is frozen already. You have thick icy mantle, and in this condition, these are optimal conditions, I will explain it to you, for large deuterium fraction. So now the D over H can reach more than 20%. Consider the cosmic D over H, which is 10 to the minus 5. And I just wanted to point out about Lin, where is here, show you. That in fact he also did very nice work on the depletion of a starless core that also show quite large values of depletion because probably it's an old starless core in hydrostatic equilibrium. So it's actually very interesting to see that these work shows that the freeze out is actually an efficient process. So you expect in this region to have thick icy mantles here with a lot of water. Of course, water is the first to form because you have oxygen that is the third, well, say chemically speaking, is the second most important and the most abundant element. Helium doesn't really participate much to the chemistry. So you have oxygen sitting on the surface, getting hydrogenated and form water very soon in this cold environment. And then you have also CO freezing out, and CO can also be hydrogenated and saturated to methanol. And then you have then a large amount of methanol, and in fact we see methanol ice in these regions. We start to see with also JWST, and of course CO2 and ammonia as well. So how does it work? So the chemistry here is very simple because it is all based on this reaction here that was studied already in the 70s by Watson, and this is an exothermic reaction, and it start with H3+, which is the most important molecular ion in astrochemistry. So as you probably know, H3+ comes from the ionization of H2 by cosmic rays, and then you form H2+, which immediately reacts with another H2 molecule, because there are many H2 molecules in molecular clouds, and it forms H3+. H3+ can react with HD, so we believe, again, like H is in H2 in molecular clouds, the deuterium is supposed to be mostly in HD form. So it's relatively low in abundance because, as you remember, it's about 10 to the minus 5 compared to H2. But still, one of the say main reaction is with the H3+ molecular ion, and you form in this case H2D+. H2D+ is then the deuterated version of this, so you have a deuterium that is loosely attached and can be given to other species, and this is how you propagate this deuterium in other molecules, okay? Now, this is as I said, is an exothermic reaction, so it means that if the gas temperature is below 30 Kelvin, and we know it's below 30 Kelvin because it's at least, say, 10 Kelvin, and going down to 6 Kelvin, this reaction cannot proceed backward, so it's not energetically favored, so you keep increasing this ratio. Then in the 80s, 10 years after this, Dargan and Lepp wrote a very short but to the point paper saying that if the gas, so the neutral molecules, say neutral species and molecules, like the main destruction partners of H3+ and H2D+, for some reason disappear from the gas phase. They did not talk about freeze out at that time, but they were talking about like low metallicity environments. You know, it could be a dwarf galaxy or some kind of early universe chemistry or something. In that case, they predicted that this ratio gets much higher than what just this reaction here can bring to you. So, and the reasoning of this paper is as simple as this. So let's focus on CO. CO is one of the main destruction partners. So if you have a CO in the gas phase, H3+ is destroyed and form HCO+. Can also react with HD, and then this will produce DCO+. When it reacts with the CO, will give a deuterium to that. But if CO freezes out, what happens? Well, you have lower destruction rates because you just have lower amount of the destruction partner. So you have a lower both H2D+ and H3+ destruction rate. You increase the formation rate of H2D+ because this is increased because you have less CO. So the sum of these two, this is the whole paper. The sum of these two is a larger H2D+ over H3+ abundance ratio. And how large? Well, it can actually reach 1. Okay, it can reach unity in your code depending on the condition. So it's really huge number. Expanding a little bit, now that before we saw H2D+, so we were stuck here, but now we can proceed and go even to D3+. Why not? In fact, I mean, actually, this has been detected, both the ortho and para form. You know, these molecules that have H2 here, D2 here, so they have these multiple forms, ortho and para, ortho para meta. So it's an interesting chemistry here going on, and symmetry of the molecule. But here the point is that in cold regions, nothing stops you to get more and more deuterated. So because you can still react with Hd and form D2H plus and also get to D3 plus. If you look at the chemical model predictions, you actually end up with time with a lot of these D3 plus, which unfortunately we cannot detect very easily because it has a frequency, it's a symmetric molecule, so H3 plus the same, we can only see it in absorption, but in diffuse clouds, because this is like around 2-3 micron, so you really need, you cannot go in a prestellar core where the extinctions are 100 magnitude. D3 plus is a bit better, it's about around 5 micron, the line, but again, it's not easy to detect, and it has not been detected yet. Anyway, once you form all these deuterated molecular ions, what can happen to them? Two things. One, they can meet with, for example, CO, and you form DCO+. This is why DCO+ is everywhere. It's very easy to form. You just have a CO and then one of these ions, deuterated ion. Or, for example, you can meet N2 and form N2D+, or ammonia and form a deuterated ammonia. This is the deuterated ammonia. The other thing they can do is to recombine dissociatively with electrons. So they actually break, once they recombine with electrons, they break their bond, and they form also, among other things, they form a lot of D atoms. So even the atomic D over H locally is increased a lot. So we talk about 30-40% D over H, again, compared to the cosmic abundance, which is orders of magnitude lower. Once you have a large value of D over H, so you have a lot of D atomic in the gas phase, instead of hydrogenating your CO, you can actually deuterate CO and form deuterated methanol. You can form deuterated water, you can form deuterated formaldehyde, and indeed, methanol in deuterated form has been measured, not just singly deuterated, but doubly and even triply deuterated. And this is a huge, so when we talk about what is the increase in deuteration compared to the cosmic, we are talking about 13 orders of magnitude. It's even too much, we don't need all this deuteration, but apparently this is what happens, and it's really efficient. So you have a lot of deuteration. This is why we sometimes call these prestellar cores like the deuteration factories. There is a lot going on in terms of deuteration. So, it's very interesting. This H2D plus we detected in 2003, the one in the prestellar core. But then with Sophia and Apex, we also were able to detect the other form. So the first one was ortho, that we detected actually with the CSO, and then the para H2D plus that we detected with Sophia, and then D2H plus, also ortho and para, has been detected. And this is important because it's important for our chemistry. We need to put some limits, constraints on our chemistry. And there is another thing that is a little bit tricky, but it's important to mention if I talk about deuteration, and this is the ortho to para H2. Now, when I told you about this Watson reaction, H3 plus HD that forms H2D plus, I simplified a little bit because it depends a little bit on this product here. So let me start from the beginning. H2. H2 is in two different forms. One is the para, and you see the para has a zero level, so the ground state is at zero energy. The ortho, which is in this part here, the ground state is at 170.5 Kelvin above the zero. So intrinsically, ortho H2 is more energetic than para H2. So when I told you before about this reaction that is exothermic going in this direction, yes, it's true. But if you have a lot of ortho H2 can actually drive back this reaction quite efficiently and kill the deuteration. So what is the other requirement that we have now? Well, we require a low ortho to para ratio in this prestellar core, because otherwise what I told you doesn't work. Okay? So if we look at this plot here that shows the abundance ratio, ortho to para, H2, as a function of time, we start with a ratio of 3. This is the statistical ratio, and this is what you expect when you form H2 on the surface of dust grains. You know that H2 forms on the surface of dust grains, and when it forms, it is formed excited, so it's hot, so you reach, say, the high temperature limit of this ratio, which is 3. So initially, you have much more, so 3 times more ortho H2 compared to para H2, but with time, and actually it takes some time, depending on the density. Here we are talking about 10 to the 5 per cubic centimeter density, so it's relatively high. Still, it takes more than 100,000 years, so you see, to become low. And how does it become low? It becomes low because the ortho H2, when, for example, react with H3 plus or also with H plus, that is present through charge exchange in this cold environment, it is transformed in para, but it takes time. So this is actually good because, if we could measure ortho H2 and para H2, we could also have an understanding of the age of the time scale. The gas was there after the formation of H2, so during the phase of, say, translucent cloud to the dense phase, and try to get, say, an estimate of the time. You see that the deuterium fraction here that is reported in this part, especially for this particular for the N2H plus, so it's N2D plus over N2H plus, it is a mirror curve of the ortho to para H2. So you need to go to below value of ortho to para H2 to get to the level of fractionation that we see in quartz, okay? So all this has been explained since a long time. The first, in fact, was Laurent Panani in 1992, then followed by experimental work by Dieter Gerlich, theoretical work by Martin Walmsley, and also Olli Sikna and collaborator. So these are the transitions. The para H2D plus that was first detected by Sandra Brunken and collaborator. This was actually a Nature paper, because in this paper I will show you, we actually measure the time scale of this region, that because we also had the ortho, so we could actually put a constraint on the ortho to para H2. I'll explain to that. So look at the frequency. This is not easy. This is something that I would love to do, in also with ALMA. And this is a dream that I don't know if I don't think it will come true soon, because this is really hard. But it's even hard to do this, but we try as much as we can. This is the 372 gigahertz for the ortho H2D plus that we did a long time ago with the CSO, but we can do with APEX and also with ALMA. Now there are several works coming out. Then we have again look at this frequency, 1.5 terahertz, okay? And this is again something that we did with Sophia. This is Joran Hardy work, discovery of the ortho D2H plus, and then this can be done again with APEX now, and also with Sophia. With ALMA. We are trying. We have not yet seen a line yet. Okay, so this is the work that I was mentioning about the discovery of the para H2D plus. So APEX was used to do the ortho at 372, and this one with Sophia and the para H2D plus. And you see the line is beautiful, very, very well detected, and also very well matched by the radiative transfer that we did based on the, say, chemistry predicted by the model of this source. A very simple modeling, spherically symmetric, but with some gradients in temperature and density. This is IDA 16293, which is a class 0 source. You need, unfortunately, a bright source, because this line is not predicted to be observable in emission. You need something bright. But if you have a very young protostar, you can expect that most of the envelope of this protostar will still retain the chemistry of the prestellar core, because it is very young, the protostar. So you can actually try to connect the prestellar phase with protostellar phase. So This is a little bit too many numbers here, but the point is that if you are able to detect ortho and para H2 plus, you can estimate the ortho and para H2 ratio. You can not estimate, you can measure, okay? You can measure the H2 over the para H2. So as I told you, this is very important because it gives you an estimate of the time scale for the chemistry to actually reach this low ortho to para ratio that we measure. And this is all coming from very simple. So there are 3 reactions that can go forward or backward with a K that can be plus or minus depending if it is going forward or backward. And so it's a very simple chemistry here. So that's why we can do this analytically, and this was done already in 2009 by Hugo, and in fact we use this chemistry for this paper here. This is the first detection of ortho D2H+. This is the 1.4 terahertz. Again, a beautiful line detected with Sophia along the line of sight of the same source. And these are all the other lines that we have detected thanks to APEX. And putting all together, we can actually have an understanding of the same chemistry. So these, in fact, are predictions from our chemical model, these red curves that work pretty well here. So, and allowed us also to actually refine the chemistry because we could also do implement. This is a bit complicated, I have to say, but in regions where you have protostars, we realized that indeed we need to take into account the excitation of your molecule when you implement the rate coefficient. So this is a work, as I said, it's a bit complicated. It is in 2017, but just to tell you that with this type of observations, you can really do some quantitative work in terms of spin chemistry and deuteration chemistry. So now we go back a little bit in time, but this is what we did. We collected in 2012 with Cecilia Ciccarelli in this review some data, and now there are more data, but still the conclusions are the same. Is that so we just collected data from deuterated molecules coming from say various protostars, and here what we have the blue, in blue is the singly deuterated species, in red is doubly, and in green is triply deuterated. So the first thing that we noticed when we put together all this data, we noticed that, yes, so we have deuteration of water. This is the D over H here, okay? There is a little bit of doubly deuterated water as well. But one thing that was really striking is that the methanol showed this very large deuteration, because you see this is the triply deuterated methanol that is more than half of the singly and well, doubly. So youngest protostars show very large deuteration, yes, but especially for organic molecules. So is this something that is say expected from the chemical point of view? The answer is yes, because in fact in 2011, and then followed by Taketa in 2012, but also more recent work by Furuya, Aikawa, and collaborator, actually we can explain this with the time. So it's the time of the formation of these deuterated species that allow us to understand. So let me try to explain. So when you actually form a dense core, you start with a relatively large, say, diffuse or maybe translucent cloud. In this region here, so at the very early phase of your dense core, so when you don't have a dense core, what do you have? You have some kind of relatively diffuse medium, so you have quite a lot of, say, UV photons. Cosmic rays are always there. Cosmic rays, they don't disappear. They continue to go through, but UV photons are more here. So UV photons are photodissociating the ice. So even if you form islands of water, you are not able to actually grow ice. So these are the cosmic rays, by the way. This is my picture of cosmic rays. But you have to go at extinction of between, say, 3 and 10, where we start to see the ice feature, like in Taurus. There are many papers that have shown that. You see water, you see CO, you see CO2, etc. This is now the outer part, the dense core outskirt. So you can also view this as a time, no evolution, so from diffuse to dense. Now here you deplete the oxygen, which is hydrogenated in water. You start to deplete a little bit of the CO. You form a CO2 through CO plus OH, etc., etc. You can hydrogenate carbon in methane or nitrogen in ammonia. However, it's only when you go in the very central region, so in the very dense part of the river, so at densities that are above 10 to the 4 per cubic centimeter, and this is extinction larger than 10 magnitude, is when you start to have this boost of freeze out. So you have this we call it catastrophic freeze out. Okay, so it's a CO catastrophic freeze out that we found in 99, but also of all molecules, they say all molecules heavier than helium that are freezing out. And I showed you before that if you have this larger freeze out, the deuterium fraction goes up. So it's only at this stage here in the dense core that is covered by CO, because CO is frozen very rapidly here, you can now deuterate very efficiently CO and form a lot of deuterated methanol. So this is, I think, is something that it's now clear. So water is formed in a region where there is not much deuteration fraction yet, okay, because there is not much freeze out in this outskirt of the dense core or in the molecular value. You have to be in the dense core to have these large values of freeze out and then large value of D over H that allows you to deuterate whatever it finds on the surface. And what it finds on the surface? CO, because it's where CO is frozen. So it's very simple to understand, and I think at least for this part here, we think we reach a point of closure, say, of the, try to understand why water is less deuterated than methanol. This was put together in 2014, so it's again a long time ago, but this is just to show that indeed, if you look at the D over H in water and D over H in organics and compare, for example, in various objects, so here we go from protostellar, crystalline quartz. Unfortunately, we don't have a detection of HDO. We tried, but we couldn't detect. So protostars, you see here, we have the D over H in organics higher than in water. I just show you the histogram. In disc, this is a little bit less clear because there is still not much, but there are some new measurements that can help here. But the important thing that we wanted to show here is that even going toward the carbonaceous chondrites and also the comets, we see now here also we have more data. We see that the D over H ratio in organics keeps always higher than the D over H in water. So it is very tempting, and this is what we did in this paper in 2014, to say that it seems that there is some kind of maintenance and of these early phases where the deuteration is so high, down to these stages here where we actually arrive at our Earth and solar system. So, well, this is very briefly, this was a work by Eleonora Bianchi in 2017 showing now the D over H only in organics, so methanol, formaldehyde, and showing that it seems that there is indeed a tendency to decrease with the time, so going from pre-stellar to class 1 and then disks. So this, for example, could tell us that our solar system, if I go back to this here, that shows the lower values of the D over H. Eleonora Bianchi was saying, well, maybe this is just due to the fact that with time we see a tendency, in fact, of decreasing, maybe because you are processing the ice and warming up. And there are, for example, a case of a warmer region here in Orion that indeed shows a lower D over H in organics. So the environment is also important. So this is the other question, is our D over H ratio that we have that is lower than what we find in young stellar objects due to the fact that it's just a very old system, or because, for example, it was born in a very rich cluster, as we think, in fact, was the case. Okay, let's leave that. It's not so important. So now we go to the comets, and the comets, these data are coming out very, very slowly. We have seen this already. This is the D over H in water. I am interested in D over H in organics because I want to see if we see the same difference between D over H in organics and D over H in water. And the answer is yes, we do. We have 2 points. So, sometimes people can say, well, you probably need more points. But it's actually, both of them are higher. The D over H here is higher than the D over H in water. So we have, as we can see now here in this more recent paper, and also the paper by Maria Grobskaya that was written in 2021, where she actually showed that indeed it's very reminiscent of this prestellar chemistry. What about these carbonaceous chondrites? So I show you these 2 points, but I wanted to give you some numbers and explain a little bit better. Yes, D over H in organics is larger than D over H in water, also in carbonaceous chondrites and in interplanetary dust particles. So if you look, for example, at the hydrated silicate, so this is where the water is located, the hydrated silicates and hydrous carbon, the D over H is exactly the same as our ocean, as I showed you before. But when we look at this so-called hot spot, where we have a larger deterioration locally, we see that the D over H can go up to 0.01, so 1%, and this is, say, getting closer to what we see indeed in young stellar objects. Okay, so some puzzles here is this is the famous large program for ALMA led by Jens Jorgensen that shows the chemistry, especially in this part here. So this is IRA 16293B, this is A, and it shows that an interesting result that is still not clear. That if you look at this is the excitation temperature of the lines of these molecules that have been detected, and this is D over H. He noticed that indeed the more complex organic tend to have a higher deuteration. So for now, we don't really know why this is the case, and the reason why we don't know is because our models don't contain yet the deuteration of these these complex organic molecules or comps in our models. So we in fact have a plan to implement this deuteration, and the student is working on that. But for the moment, it's still not clear why this is the case. And even in high mass forming region, we have, it seems that the highly deuterated objects are the ones without stars, so the so-called high mass starless quarks. So this is the diffraction of 0.26, this line here. These points are in fact the high mass starless quarks. These other are either high mass protostellar objects or ultra compact H2 regions, so they all have lower deuteration. So there is an evolution in time. So this deuteration is something that you can use not just for low mass, but also high mass star forming region. And I would like to say, of course, now we have protostars and planet 7, and there is a very beautiful review led by Nomura, where in fact you can now find an updated version of these plots. The conclusions are the same, so it's great. I'm happy about that. But of course, this is a much more detailed, looking also at the meteorites and planets and satellites. So you can see that organics have a higher D over H compared to the water. So depending if it's blue or red, etc. But I just wanted to give you this in case you have not read it. You should read it. So in the last 10 minutes, I'll give you some updates on the 15N fractionation. This is a bit more complicated. But we are very interested because I said that, again, this is some link that really can tell us about our origins. So it's important that we understand. So let me start with this plot that is similar to the deuterium plot that I showed you before. So now, to make things more confusing, and I really don't understand why we do this. For the D over H, we put D on top and H on the bottom. So you have small numbers, okay? Here, for the 15N, we do the reverse. So please bear that in mind, because now you see very large numbers, and you say, oh, this is a lot. No, it's low, okay? So it's, but these are historical reasons, and actually, if you talk to people who work on the solar system, they don't even use this. They use delta 15M, which is a complicated formula, which, okay, it's not a complicated formula, but it's related to that. But in some interesting way, they have to put inside some values related to Earth. Anyway, don't look at that, okay? Just look at this 14N, 15N, and this is our starting point. PSN, protosolar nebula, this is the value that we have based on also measurements, actually, of our local interstellar medium. And what we have is that you see this ratio is about between 350 to 70, and in fact, we have this in Jupiter, we see this in the solar wind, and we have some values that are similar to the protosolar nebula. For example, in prestellar cores, for specific molecules, in particular with molecules that they have this NH bond, okay, N2H plus or ammonia. In this case, we have values that are more or less this, or as we will see for N2H plus, this would be even higher, this value. So this means that you have low 15N, okay? Now, to find the comets, you have to go up here. So now you have a lot of 15N in HCN, CN, etc. in comets, and also in IOM is the insoluble organic matter that you have in this refractory component of the carbonaceous chondrite. This is the soluble organic matter that contains mostly amino acids, okay? So, and the Earth is here, okay, it's high, so this is the N2 in our air. It is fractionated. And the interesting thing that Hillebrand said here in this paper when he did this kind of review is that there is a differential 15N enhancement depending on the type of molecule. So if you have CN bond, you have fractionation. If you have NH bond, you don't have fractionation or even anti-fractionation, as we will see. So, fine, let's compare now with other things. Unfortunately here for the comets, we don't have this NH bond to relate, but it's interesting that in starless cores we have the same high HCN, but low NH. Okay, then if you want to know for protostars, you see there is a lot of fractionation in protostars. So this was an observation by Susanna Wonfler that did in 2014, and for protoplanetary disk also there is an interesting large fractionation measured with HCN by Gutzman et al. What about our solar system primitive material? Interestingly, again, it's the same. It's very similar. So we find in this hot spot large 15N excess that is found, for example, in meteoritic material, interplanetary dust particle, cometary dust particle returned by stardust. We go down to 65, so huge amount of 15N compared to the protosolar nebula. Now, one could ask the question, are these hotspots the same as we have with deuterium? Are in the same location? The answer is no. There is no correlation. And in fact, we don't even see correlation in our, say, prestellar object. If it is highly fractionated in deuterium, doesn't mean that it is highly fractionated in 15N. Actually, it's totally the opposite. So it goes in the same direction. And more recently, 2017, this is, I think, super important, because remember, Hillebrand noticed that there is a difference in the fractionation depending if you have CN bond or NH bond. Here it is. Van Putten et al. They found that in meteoritic material, 15N fractionation is larger in CN than in H2 and NH. So again, we go back to our, early phases of star formation. This is complicated, but it's good because it's wrong. So you don't even need to memorize anything here. So in fact, I say that this is the old picture. We tried to understand this fractionation originally before actually we made detection of 15N. These were predictions. say, okay, we predict, this was Rogers and Charlie, and also Tertiary helps, that there is a fractionation. So if N2H plus, N2 with the main isotope, 14, and encounters 50 N, there must be some exchange that is exothermic, so then this will increase the fractionation, and so we predict that the 15 N2H plus over 14 N2H plus will be higher, and actually we see totally the opposite. So this is, that's why it's important to do model, but it's also important to do observations, because otherwise we don't progress. In fact, in 2015, Evelyn found with the quantum chemical calculation that the reactions that I showed you before are not proceeding because there are barriers. These are barriers. They have barriers. They don't go through the N2H plus at all. So if you put these new rates in models, doesn't work. Nothing works. You cannot predict any fractionation HCN, and you cannot predict the low values of fractionation N2H plus at all. So it's really sad. I mean, you read this paper, and after that you say, okay, maybe it's better I work on something else. But of course, we wanted to understand, so we kept doing observations, and this is the work by Elena Redelli. We started in 2013 with our prestellar core, where we found F1544 very high values. So this means anti-fractionation, okay? Anti-fractionation, totally impossible to reproduce with chemical models. And then here, Elena put more prestellar cores that are a bit lower, but still higher than so it's still an anti-fractionation compared to the local ISM that was in fact measured by Laura Holtz in 2018. If you look at protostellar objects, what you see that prestellar cores are here. These are the protostars. Yes, they tend to go down and reach the say protosolar nebula value. So doing these observations here, then people like Lozon in 2019, and they actually said, well, we can probably explain this if the 15N and 2H plus dissociativity combined with electrons faster than 14 and 2H plus. Now, if this is true, yes, it will work, but nobody has measured this, so we have asked Heidelberg, because they have a nice cryo ring that they can measure, to see if this is the case. The prediction from the quantum chemistry says, no, this cannot be true, because the 14 and 15N are not so different, so you don't expect. So it's still a little bit up in the air. They must say, I think we are getting to the point that all this is due at the end to this photodissociation. Selective, so consistent with isotope selective photodissociation. So let me try to explain here. So these are maps that have been done very recently. It's very difficult to do these maps. That's why they look ugly. Sorry, but it's really hard. It's very long time to get the 15N and ammonia or 15N HCN in this prestellar cores. But we see that in the outer part of the cloud, this is the prestellar core F1544 again, we see that the fractionation, so in this case 14N over 15N, becomes lower, so you have more 15N in the outer part, and this is the case also for HCN, while going toward the center, you get very low value. We think that this is due to the fact that in the outer part, you preferentially dissociate when you have N2. N2 can self-shield because you can have large amount, say, of N2. But if you have a 15N and 14N, so the 14N, 15N is not self-shielded because the abundance is much lower. So it can actually dissociate, and you can have more atomic 15N that can produce ammonia and can produce HCN, while the N2H plus that we form from N2 will be actually mainly 14N. So that's why. So I'm telling you this because we are working at the moment. Yuri Aikawa and Furuya have also mentioned this, but they still cannot get this large anti-fractionation that we have with the N2H+. So it's still work going on, but I think we are in the right path to try to explain this. So it makes sense. It makes sense because in the outer part we really have more UV photons, and this selective photodissociation is isotope selective photodissociation. It makes a lot of sense. And in fact, it is seen also. This I skip, but this is similar to the previous slide. So also in high mass protostars, we see that there are variation in fractionation in N2H+ that is consistent with the isotope selective photodissociation, because we have larger fractionation toward dense region within high mass protoclasses, while in the outer part you have say more UV. Here it's a beautiful, this is a work from Hilly Plant. It's a beautiful work with ALMA from TW Hyder. This you need to see because I think this is the first resolved map of the fractionation with HCN. And you see that going from 10 AU to 60 AU, you have this increase in fractionation. And this is again due to isotope selective. This is very clear. You have the young stellar object here, and then here you have more photons that actually dissociate the nitrogen, and you can have more 15N for HCN, so you enrich this, so the ratio becomes lower, and then in the outer part where you have less photons is less. But even Hilly Blunt says, yes, this makes a lot of sense, but my models are not able to quantitatively reproduce this. So we are all still in the same boat that I think we are still missing something crucial. And he's talking about these different nitrogen reservoirs, because in fact we see different values of fractionation in the inner part of the protoplanetary disk and in the outer part, but also different molecules show different values of the 14N over 15N. And the interesting thing, if you look at that, is that also in our solar system, we see very similar thing. There was this beautiful paper by Jewel, Dasgupta and Marty in 2021 in Nature Astronomy. This is the famous delta 15N. So in case you want to do your translation, this is so this is the sample, and this is the atmospheric. Let's not discuss about that. This is the final thing I wanted to say. So in our solar system, you have the carbonaceous chondrites, the ones that are deuterated, the 15N fractionated, etc. In fact, they have this larger value of the fractionation of the 15N. The non-carbonaceous chondrite, that is the other very significant population of chondritic material that in fact has contributed to the formation of our Earth as well, they have much lower values of fractionation. So they also, in this paper here, they talk about this isotopically distinct or different reservoir of 15N. And they say that, well, the Earth is in between, so I deduce that the Earth is made of a mixture of these two. That's easy, huh? Okay, makes sense. Okay, good. So let me then here conclude with this other plot again from the same paper as before. They talk about all kind of fractionation from D over H, 14N, 15N. So it's a beautiful review because they really have updated the plots that have been done before. So my conclusion for you to remember that the larger deuterium fraction are present at all phases. There is a bit of a decrease going to more, evolved system, but still it's a larger diffraction compared to the cosmic D over H. And it's always true that we have this D over H in organic larger than D over H in water. So this is indeed telling us that there must have been some storage of pre-stellar ice, and this pre-stellar chemistry is important also for later phases of planet formation. For the nitrogen isotope selective photodissociation, we believe now that this plays a crucial role in the fractionation. There is no other way to actually understand this fractionation and anti-fractionation that we see. So we also notice that there are multiple nitrogen reservoirs, so different 15N fractionation depending on where you are. and also depending on the molecule that tell us about these fractionation processes. And these have been measured in crystalline, quark, protoplanetary disk, and solar system. Again, this is giving us this idea of inheritance. So to make it in a pictorial view, you really need, if you want to understand not just us but also planetary system, and hopefully when we will be able to detect the deuterated and 50N fractionated molecules in an exoplanetary atmosphere, we wanted to really take into account these previous phases that are very important. Don't start from your isolated disk. This is what I want to say if you want to understand the chemistry and the planet atmosphere. You need to start much before that. The initial conditions are super important. And the puzzle, just for you to remember, so the Y complex molecules are more deuterated. This is something we still don't know. It's also not clear if the lower D over H measured in the solar system material is due to the temporal evolution. As I show you, maybe it goes down because it's warmer, I don't know. But also could be that initially our solar system was already poorly deuterated because it was formed in this warmer environment in a massive cluster of stars. And the final thing is really how to explain the larger 50N antifractionation that we see in crystalline cores, and this is still something that we need to find out. So I'm sorry I'm a bit late. Thank you very much.
Thank you. Questions?
So in the nitrogen fractionation, so the HCN is measured, but what about the HNC? Yeah, the HCN form in the warmer temperature. Then in the cold temperature, the HNC abundance is higher.
Yes.
What about the fractionation in HNC?
Yes, so that's a good question because I think I have it here. So we didn't do survey yet for low mass, but for high mass, there have been already measurements. I skipped this, so you couldn't see. But also in HNC, there is a range of fractionation that has been measured. So you see, it's like it goes from relatively fractionated, because remember the protosolar value is about 370, to almost anti-fractionated. So you see almost everything, depending on the environment. It's not so different from HCN. So I think the two, although the HCN can actually reach significantly lower value. So this, from my point of view, this is telling us that HCN, as you said, can also be present in warmer environments. In these warmer environments, probably this means it's more irradiated, so you have more of this isotopic selective photodissociation. You can reach this low value. HNC that only form in protected region, it cannot reach these low values here, so very large fractionation, but still can probably get inheritance from the HCN in some regions, and can also be anti-fractionated like N2H+. So there is some difference.
So Paola, do you think there's any resolution effect?
Resolution effect, okay, so for these high mass star forming regions, indeed there is some problem with the resolution, because so these values here that I'm showing you for the high mass, they are all made with single dish, and in fact, if you look at this, that is the slide that I show you, that is done with NOEMA. So now we have a higher resolution, we can actually resolve the core, the dense core here. We see indeed that with the single dish, you see this region all together. So you're just getting an average value. But what Laura Cozzi found in this paper with NOEMA is that indeed the 15N fractionation changes if you are in the core or if you are in the outer part. So it's very important. You really need, so that's why so far I think people have been focusing on nearby, so torus cores, and the high mass is a bit more tricky. Yeah. But still, if you can use Moema or ALMA, I think you can do it very well. And the disk is the same thing. For the disk, you really need to go to super high resolution to do this. So that's also, in fact, a problem if you want to extrapolate. Again, if you just have a large beam, you have just an average value, but here you plan to show that you have this typical.
Yeah, you do have a
yes.
gradient.
If you take the average, you're just in between, and you don't see anything interesting. You say, oh, it's not fractionated, but actually, yes, it is, but very close to the star. So it's super important. You need to do it, with high resolution.
Hi, very nice talk. So I would like to know from the 15N fractionation or from the anti-fractionation, is it possible to probe the evolutionary stage for the crystalline core objects or even for the protostellar objects? I know you showed a figure previously where you had the anti-fractionation over the different protostellar objects. Yeah, this one.
Yes, this one. So yes, it seems that there is evolution, no? It could be nice to do, so again, a very interesting question. We have not done it yet, you see? So that's, I cannot answer. I can just say that we see evolution if we go from prestellar to protostellar, but it could be nice to see, for example, if you have an evolution even before, no? So, say really if it is stardust, so at which stage or which age your core is. And that has not been done yet. And I think the reason is that the 15N molecules are really faint. And so it takes many hours to detect, say, in prestellar cores that are centrally concentrated and bright. For starless cores like the one you have, I think you had the L1512, that has a lower density, central density. I think for that it could take, I don't know, maybe 30 hours of integration. It's possible, but it could be interesting actually to do that. So far we can say that, for example, if you wanted to do like a blind survey, I don't think it's a good idea because it will take thousands of hours. But anyway, if you want to do it in the future, we will have a very sensitive telescope, and we can do that. And you want to do a blind survey, definitely the 14N, 15N in a 2H plus that shows this large anti-fractionation will tell you that you are in front of a crystalline core. So that would be interesting to do. But again, it's a bit time-consuming.
Thanks for the explanation.
Any other questions?
It seems that the photons are playing an important role in the nitrogen fractionation.
Yes.
So I wonder if you look at the environments of all these cores, do you have extra flux of the cosmic rays or UV radiation or whatever? It's an environment issue. And also the mass of the star, the stellar environment.
Yes.
Other massive stars, I think these all need to be considered.
Exactly. Yeah. That's definitely a very important point that, for example, in this case here, which, okay, I don't have the larger map, but this is this core that I showed at the beginning, in fact. Actually, so just remember this and then I go to another slide. So this is the fractionation of a 15N. So we see that there is a significantly higher fractionation here in the south, no? In this part here of the core. Now, if you look at the larger scale environment, just imagine that indeed in this part here, south and this region here, there is basically the edge of the cloud. So this is where we say, where we can say that this part here is more exposed indeed to the radiation, interstellar radiation field. Cosmic rays, I'm not sure because we think that cosmic rays are not able to, say, get, so they should go through because the column densities are not so high. You know, we're talking about extinction of AD of, say, 100 magnitude.
H3+ is ionized by cosmic rays.
Yes, so you need cosmic rays, but what I'm saying is that we don't expect significant difference in the flux going from, say, here to here, just small variation. And what is more changing is the UV flux. So you will have a low UV, say, very low UV flux here, and high UV flux in this part here of the core. And in fact, what we see in this region here is also an enhancement in the abundance of molecules that contain many carbons. And to make these many carbon molecules, you need to photodissociate CO. And so it makes a lot of sense, basically. So yes, you need to have more photons. And the other one is this one, that in fact shows that the fractionation changes if you go to the dense region or in the outer part of the core. Now here we are in a high mass star forming region. There is some illumination around, so it makes a difference. In fact, if you are inside protected or if you are outside. And again here we believe most of the damage, say, or the change is done by UV. So it's very important to look at the environment.
40 years ago, I did some work with Bill Watson on the chemical fractionation of 13CO and
okay.
And it was looking at some regions around H2 regions. So the photodissociation was very important there.
Exactly. Yes, yes, yes.
So I wish Bill Watson is still alive to share some wisdom to us.
Yeah, I mean, he was a pioneer.
Yeah, right, yeah. We miss him.
Definitely.
Any last question? If not, thanks.
Thank you.